Namaskar and welcome to the course on basics of geocomputation and geo web services. I welcome all of you for this course number 128 and module number 4 of course number 122. So today we are starting this particular course, and this is a 1 week program, and in this 1 week programs we are going to discuss the basic course contents on the geocomputation and geo web services technology and applications. This is the first topic what I will be taking today, and second topic what we will be discussing in this course is open geodata repositories and ISRO geo web services for thematic applications. Here my colleague will be discussing with you about the different data products and services from ISRO and also other sources from where you can directly access the data and information for various thematic applications. Then we'll be discussing about the programming concept for geocomputation, where we'll be giving a introduction on the Python and R, how these two programming languages and platforms can be utilized for geocomputation purpose. So here one introductory lecture will be there, and then we'll have the session on overview of web GIS and its applications, where we'll be discussing about the different technologies which are readily available for web GIS applications, and then we'll also tell about different type of case studies, especially by using this web GIS technology, how the data dissemination, data processing, data analytics can be performed in online platforms. Then we'll have one session on the cloud-based geospatial data processing, where we'll be discussing more on the cloud computing part. And in the cloud computing, we'll be taking a case study or a demonstration based on the Google Earth Engine, how you can utilize this cloud computation-based platform for geodata processing and analysis. The total course duration of this course will be around 7.5 hours, as we'll be discussing 1 hour basically lecture session and another half an hour for the discussions, or basically discussion or interaction on your questions. So this way the entire program will go, and I again welcome all the new participants. Those are basically joining in this course number 122 on the geocomputation and geo web services, and also the participants, those are basically continuing from the last module, that is module number 3. Now we are in the module number 4 on the your course on basics of remote sensing in GIS and GNSS technologies. So today's topic is on the geocomputation, online GIS and geo web services. What are these technologies? What are these terminologies? My name is Harish Karnatak. I am head and scientist SG in the department called Geo Web Services, IT and Distance Learning in IIRS, Dehradun. So let us start with the basic concept of geocomputation. And you know that the basic understanding, if you try to understand this geocomputation term, it is with the geo and computation. These are the two words we are combining together. When I say that geo, that means it is related to geography or geographical data, and computation is a computation, where we'll be basically talking about the computation with geographical data. So basically, if you try to understand the definition from the literature, it is the art and science of solving complex spatial problem with computers. When I say the spatial problem, spatial means the problem which are related to space and time. So the terms spatial means we are talking about space and time. So this is one definition. Second definition says that this is the process of applying computing technologies to geographical problems. So this is again a definition given by Ridge and Turton in 1998. It says that geocomputation is a technology or a method where we are applying the computation technologies for geographical problem. Another definition says that it is a computational theory of complex socio-temporal processes. Let's talk about the social temporal process. That means we are going to solve the complex societal problem which are changing with respect to time. So it is known as a socio-temporal processes. Then another definition says that geocomputation is the way in which new computational tools and methods are used, also fundamentally about the depiction of spatial process. Again, here we are talking about the solving the spatial problem. It's talking about the spatial processes. These are the few definitions what I have taken from the literature, but if you try to again study the literature, you will be getting more definition. But in general, if I summarize here, it is a computation methods. Basically, we are applying on geographical or geospatial data. When I say the spatial data, that is a data which is basically related to space and time. Now, typically, we are combining these techniques, and then finally we can make a statement like geocomputation is a method to use computations for processing and analyzing geographical data for information extraction and decision making. Because basically the objective of geocomputation is information extraction and also the decision making. So when we do the information extraction, then we of course apply the different methods of information extraction, which may also include some of the algorithms or some of the models which will be used for this purpose, so that we can extract the better information, or we can take the better decision for any planning activities. And if you try to understand further, the Sten Openshaw is the generally recognized as the father of geocomputation. He stated that geocomputation is about using the various different type of geodata and about the developing the relevant geotools within the overall context of scientific approach. So basically, we are using geographical data, geospatial data, and applying the geotools or geographical tool in the context of the scientific approach. He has also identified three aspects that make geocomputation special. That is, first is a emphasis on geo subject. That is a geocomputation is a concern with the geographical or spatial information. Second terms, what he focus on is the intensity of the computation. So it required basically a lot of computation resources. It allows new or better solutions to be found for the existing problems, and also let us solve problem heretofore insoluble. And finally, geocomputation required a unique mindset, because it is based on the replacing vast amount of computation as a substitute for missing knowledge or theory, and even a augment intelligence. So when we are applying the geocomputation technique, we also require the knowledge of a domain or the subject related to which we are going to solve the problem. For example, if you are applying the geocomputation technique for urban planning, for disaster management, for agriculture, or maybe geological application, so then you should have the knowledge on this thematic domain as well. But since it is generally not possible that all the computation experts or geographical expert will be also be expert in the thematic domain, but in that case what we can do, we can include these thematic expert in our team. As a teamwork, we can apply the geocomputation technique to solve the specific problem of a particular theme. If you see following four questions to be most important with respect to the defining the definition given by Sten Openshaw et al. This is that what we required here in geocomputation, what we have to understand here. Is there any focus on the high performance computing? Are we talking about the applying the high performance computing or cluster based computing for solving the problem? Second question could be, is geocomputation simply a grab bag of tools, or what is the relationship between GIS and geocomputations? What are the key concepts of geocomputation? These are the basic four questions what we will try to understand during this course. So here we will see how the high performance computing or cluster computing based solutions are really useful for the geocomputation problems. And today, if you see, the advancement of geocomputation has emerged as a domain called data science or spatial data science, where we apply the geocomputation technique or for analysis of the geospatial data or any type of data to get a or to extract the hidden patterns or hidden knowledge from the data. So here the geocomputation methods are very very useful for applying in the problem like in a data science where we look for inside the data. So what kind of information we can extract or we can basically discover what kind of knowledge from these data sets. So before that, now we have to understand, especially for the participants those are joining this course first time, now we have to understand what exactly geodata is. How we can say that a particular data is a geodata? What are the characteristics of this data? Typically, we know that when we have the data or database with us, then we basically need a database management system or database system to organize and manage the data. And here typically the relational database management system or object-oriented relation database management system or these days NoSQL database systems are already available. So what are the unique features or geodata that we will try to understand now? Typically, if you see the spatial data is a database that is optimized to store and query data that is related to object in space, including point, line, and polygon. These are the basic data geometries that what we use in the geodata to store and manage our geographical data as a vector data, or sometime we also use the pixels or picture element to store our raster data. While typical database can understand various numeric and character types of data, additional functionalities need to be added for database to process special data types. Basically, if you try to understand the relational database management system or simple DBMS, where we store the data in the form of data types. The standard data type could be your text, number, integer, float, double, or maybe sometimes varchar, varchar2, all these data type we use in our database management system. But we do not have any specific data type for the geodata or spatial data where we deal with the vector and raster data. If you want to store your vector and raster data inside the database management system, then you require a specific type or a specific facility to store your geometry data type into your database management system. For this purpose, you have to have the facility of object orientation inside the DBMS, so that you should be able to create your own object, and once the objects are created, then you can store your vector like point, line, polygon, or raster like a image inside the database management system. Once you are able to store and manage your vector and raster data inside the DBMS, then you can apply a typical structured query language for different type of operations like select, create, or maybe what I can say around DDL, DML, or DCL. These are the different type of statements what we write in the SQL. You can simply apply all these statements and you can perform basic data analysis by using simple SQL statements. So then once it happens, then what we can get here, in addition to that simplifying the query, we can also or we should also have the function like spatial measurements, like find the distance between 2 points, polygons, area, and so on. We can create the special functions like modify the existing features to create the new one. For example, by providing a buffer around them, intersecting features, and so on. So what we can do, we can create a new special functions, and these functions can return a different geometries to us, and this geometry could be point, line, or polygon, or maybe simple pixel edge. Then we can also we should also be able to do the special predicates like allow the true or false queries, such as is there a residence located within a mile or within a kilometer of the area we are planning to build a landfill. So if you are planning to fire this kind of query, it should allow or to run a Boolean operator with special context. So these features will be required especially for the spatial database management system. It should also have a function like constructor functions and the constructor function inside the DBMS. What this constructor function will do, it create a new feature within SQL queries specifying the vertices. These are known as the point of the nodes, which can make a line or it can make up a polygon. If the first and last vertices of the lines are identical, then feature can also be type of polygon. So that means the special database management system must have the facility of constructor function, so that I can create a new feature based on existing one. So by applying this query, a new feature can be created here. The another function what will be required to us in the DBMS called observer functions, and these are the queries which return the specific information about a feature such as location of the creator of circle or center of the circle. Suppose you are simply calculate what is the centroid of a particular circle. So through the SQL query, we should able to fire or we should able to call this function, and the return it should return the answer as a simple geometry or a simple coordinate. So due to these special characteristics and specific query requirements, a standard database management system may not be sufficient for storage and management of special data. However, many industry standard RDBMS packages are now supporting special object inside RDBMS. So suppose you are taking MySQL or PostgreSQL or DB2 or Oracle, any database management system, and you are willing to store your vector data, your raster data inside the DBMS. These days, these standard DBMS or RDBMS are allowing you to create an object for the vector, create the object for raster, and then you can easily store your geographical data inside these DBMS, and then you can use the structured query language for analyzing this data, and also you can present the output in the form of the KML or JSON file or XML file, and so. This is a basic concept of vector and raster data, and you know that how these data sets are stored and managed. You can see here typically the vectors are in the form of the point, line, and polygon. So typical examples are shown here. You can see the x and y coordinates are shown here. If you want to represent a point, then like a x comma y, so here it says that 2 comma 2, so this is a point location. Simply if you combine the multiple point together, then you can create this particular object as a line, and when you have this line geometry with you, then you can perform different type of line operation with this particular data structure. So like you can measure the distance between 2 points, or you can generate the buffer around the point or buffer around this line. So this kind of geometries are used in GIS basically for the linear features like river networks, roads, so where or transmission lines, there you can very easily use the this kind of geometry for basically representing the geographical data. Simply another the geometry which we use is called polygon. Here you can again see that multiple points are connected together, and when you are connecting these points together, then you will have this area, and you can perform the operations like you can calculate the area of this particular boundary. So this geometry is very useful for the geographical feature where we look for the area calculation, especially like you want to calculate the area of a playground, or you are interested to calculate the total area of the forest cover, total area of the agricultural land or crop land. So this kind of features are very important or useful for various thematic applications. So depending on upon our requirement, we use these geometries, and these data set we call it as vector data sets, and we can store the vector data inside the DBMS or RDBMS, and of course in the NoSQL database as well, and then we can perform the different queries like SQL statement and so on, and we can analyze this data. The another data model which is very popular or very important in the GIS or the spatial data is called raster data model. The representation of the same point, line, and polygon in raster is also shown here. You can see here, here the values are basically shown in the form of the pixel. So here suppose you are representing point, then you will be covering that particular pixel, and otherwise if you are representing the line, the line feature also can be represented into the pixel, but the complete the pixel is covered by these values, and then line features are shown here. Similarly, for polygon feature also we can represent in the raster data that there we will be capturing all the pixels which are basically occupying or showing the same values. But here you can see the difference. In case of vectors, we are able to define the boundaries very nicely. So here boundaries are very nicely defined, but in case of pixel, the boundaries are not clear, it's a fuzzy in nature. So it depends on the applications, what type of applications we are going to perform with this data. So accordingly we opt for the data models. So both the data models are having their own advantages and limitations. So depending on the requirement, especially where we require the continuous surface, then we go for the raster data. Where we require the discrete boundaries, there we go for vector data. So there are many benefit if you try to understand a little bit more on the vector data. The advantage of vector data format is allowed precise representation of the point boundaries and linear features. So basically precise representations are possible through the vectors. It is useful for analysis tasks that required accurate positioning. For defining the spatial relationship, you can also use like connectivity, adjacency, and these relationships typically be called as a topological relationship. So where we require the topological relationship between these geographical features, then we use the vector data model. The main limitations or disadvantage of this vector data is that the boundaries of the resulting map polygons are discrete, so enclosed by well-defined boundaries, where in the reality the map polygons may represent the continuous gradations or gradual change, like for example in the soil map, rainfall, temperatures. So in many places the boundaries or drawing a boundaries are very difficult, because ultimately in these data sets or data models we are trying to basically do the abstract representation of the reality. So whatever we are seeing the geography, we are trying to transfer this information to our computer system. So in that case it will be very difficult to basically represent the many geographical features in the vector data where we require the we do not have any boundaries. For example, temperature, we cannot draw the boundary like after this boundary the temperature will change, or similarly for rainfall we cannot do it. Similarly for soil maps. So in some cases it's not possible, but in some cases the vector data models are perfect or very good for data analysis. For example, suppose you want to represent a road, a line features. So here suppose you want a distance between 2 points, then you may not require the polygons here. You require only the line features, and line feature will make it very simple to analyze these data set. Similarly for the cropland, the forested land, or maybe other or land record management, especially for our cadastral maps where we require the exact boundaries, there of course this data model is very useful and effective. In other side, if you take the example of raster data, already I discussed about it. It is basically shows the continuous features like soil moistures, vegetations, ground temperatures, where we do not have the discrete boundaries. There we use the raster data models. And here satellite imagery itself, or aerial survey or drone imageries, they are basically capturing the geographical data in the form of the raster data models. They are taking the images, or these images are basically storing the information in the form of the pixels. And here the quality of the images depend on the resolution of the pixels or picture what we are storing here, and depending on the pixel resolution the information will be gathered and collected, and then further we can utilize these raster data model also for different type of applications, especially for the geographical feature where we require the information to be presented as a continuous information. So in that case the raster data model will be effective. So these are the another examples how the rivers are shown in an image, and the same image if you try to understand how it will be stored in the computer system, then you can see here this side you can see here this is a water body for example, and the water body in the form of the pixel, it is stored in the computer system, and the pixel values here, it shows that the value of the water. Other places there is no water. Similarly, for the road features, we have the red kind of pixels here shown here. It can be stored. So this is the method basically what we use for storing all these data sets, either as a raster or vector data. Another important thing what you need to understand in the spatial data is a projection, scale, accuracy and resolution. These are the important parameters what we should keep in mind while creating or storing or managing the geospatial data or geodata. So projection is a method by which the curved 3D surface of the earth is represented by x and y coordinate and on a 2D flat map or screen. So here of course distortion is inevitable. There will be something we have to lose here, but because ultimately we are converting our 3D surface into 2D flat map. So this method is called projection, and today we have thousands of projection systems available with us, and in fact we can also customize our own projection system. It is a mathematical process to present the 3D surface into 2D surface. So there are different methods are available that we have to keep in mind, which projection system will be useful for our own application. Another important thing what we should keep in mind is the scale, the ratio of a distance on a map to the equivalent distance on the ground. So when we are storing the spatial data into our computer system or creating the spatial data, that time the scale is one of the parameters which will basically tell you the quality or accuracy of your data what you are storing to the system. The accuracy is how well does the database information match with the real world. So here we have a different type of accuracy. One is called positional accuracy, second is called consistency, third is called completeness. When I say the positional accuracy, it talk about how close are the feature to their real world location, how close it is in the real world. Because if I am saying that this is a geometry of a road, and the road what I am representing in my data, how closely it is matching with the real road in the our terrain. So this is called positional accuracy. If there is a shift in the position of a road, then we will consider it as an error in our positional accuracy of our data sets. Consistency is, do feature characteristics in a database match those in real world. So here the consistency is, suppose I am representing a road in a database, really it is a road in the ground. Sometime if it is a mismatch or is a classify, it may not match here. So here the consistency is another important parameter which will be considered here. Another thing is a completeness. Suppose I am talking about the roads, and for my city like a Dehradun, I am creating a road data or road network. If I am digitizing or I am creating the database of all the roads of Dehradun, then it will be called as a complete database. If it is not, if all the roads are not covered in the data, then it is called incomplete data. So completeness is another important parameter whenever we are creating the database in the geospatial domain. So completeness plays a very, very important. Otherwise, we cannot conclude or we cannot take any decision by using this data if data is not complete. We can do the decision, but the decision will not be considered as a scientific decision or scientific plan, because here we do not have the complete data set with us. Another thing is the resolution, the size of the smallest features able to recognize by the system. You know that we are using the resolution term in our mobile itself. What is the resolution of my camera? So basically how precisely, how smallest feature it can capture. This is a capability here. But in case of geospatial domain, it's not only the spatial resolution. Here we talk about the spatial resolutions, radiometric resolution, temporal resolution and spectral resolution. These four resolutions will be important for us while creating the geographical data or geodata. So here once we have the data, we have the a database system where we are able to store and manage the geographical data. We are able to use the SQL or other methods to analyze this data. But after that, what next? We require a technique called geomodeling. So this is the power of geographical information system or GIS, where we can model the this data for our future scenarios. And you know that what is model? Model is a abstract representation of the reality. In case of spatial data, spatial models, a model of some process operating in space and time. So if you are defining a process, how the process will run or operate in space and time, and there is a variation across the space and through time, and location is very very important. The result of modeling change when the location change. Location must be known here. So here try to understand, suppose you are trying to model the future scenarios of my city. For example, you have a city database and you have the historical data of all the growth or all the development of a city. Then you can model it how my city will grow in future. What will the future model for the city? So this will be called as a spatial model. So here is a very very important, because we are studying the this data set with in a space and time, and how things are changing with respect to time. But suppose I develop a city model or city growth model for a particular city or a small town. It may be applicable only for a small town, because in the model will change when the city will become the metro cities or bigger cities. The scenario will change depending on the location, the space, time, and location. This all three parameters are very very important. The scale and digital model, what you have to understand, the digital model don't have scale factors, but they operate at limited spatial resolutions, and the spatial resolution critical factor, it determine what is left out of the model. The cost of the collecting data and running of the model, which is playing very very important role here. It contribute to the model accuracy, the degree of uncertainty about the real world created by the models, and the temporal resolution is important for the same region, because when we are studying the particular area or location with respect to time, then how things are changing in due course of time. One thing is we can analyze based on the historical data. When we have the historical data and current data, then we can model for the future scenario as well. So where it will be required, suppose you want to make a plan, or you are interested to make a development plan for your city. So based on this historical data and current data, you can plan it and you can make a effective scientific plan for execution in the ground. So this way, these modeling exercise are very very important as per the geocomputation is concerned. Here the question comes, what will be required, analyze or model? So when you require analysis, then you will be talking about the static, one point in time, searching of patterns, anomalies, generating ideas and hypotheses, and evaluating the data. So in that case, you will be using analysis. When you require a dynamic or things or multiple point in times, implementing ideas and hypotheses to compare to the real world, experimenting with scenarios, then you require the modeling. So here in the geocomputation, we do the two exercises. One is data analytics, second is data modeling. So when we apply the analysis, it is shown here. When we apply the modeling, also is shown here in the screen. Then another terms what we use the geocomputation called simulation. So simulation is a very very important exercise, basically for the generating the virtual scenarios or live scenarios or sometime constructive scenario. So here modeling is the act of building a model, and simulation is the process of using a model to study the behavior and performance of an actual or theoretical system. While a model aims to be true on the system it represents, a simulation can use the model to explore a state that would not be possible in the original system. So here you can understand here, when you apply the modeling exercise, we have the three type of model in practice. One is called physical model, second is called process model, and third is called mathematical model. But in case of simulations, again we have the three types called live, virtual, and constructive simulation. So you have to understand that when you apply the geocomputation technique with geodata, the modeling and simulations are very very important activities what we need to execute here. So modeling and simulation, these two activities we do by using this geodata, using this geocomputation approach. So there are different methods are available in geocomputations. Well, it's called geosimulation. Then cellular automata or agent-based models are available. We have the artificial intelligence and machine learning techniques, artificial neural networks, we have the evolutionary computing techniques or automated zoning, redistributing, we have the cluster hunting, interactive data mining tools, and then we have the advanced raster processing techniques, and so on. Basically, here the in the current scenario, the term data science, what we use basically to get the insight of a data, the same geocomputation techniques are used in the data science. Data science basically combines geocomputation, statistics, and mathematical approach together, and it represents the output or the data for planning and decision making. So these techniques are available, are very popular, and the experts from the geospatial domains are very frequently using these techniques for geocomputation purpose. And today we know that we have a lot of data. So when we are generating huge amount of data or big data, in that case, geocomputation techniques are becoming very important here. This is just a scenario how the data is creating. In 2020, it was reported that the people created 1.7 MB of data every second. So this is a scenario. Every second, around 2 MB data we are creating. And this, if you read it I have taken from the literature. It says that by 2025, the amount of data generated each day is expected to reach around 463 exabyte globally. So when we have such huge amount of data with us, it's very important to develop the techniques and method to analyze this data or to extract the meaningful information from this data, because storing of this data for archive purpose will be very difficult. Ultimately, we required the information or hidden patterns from this data set. So here the term big data is emerged, and today we are using big data for many applications. You know that what is the characteristic of this data? Big data is like volume, variety, value, velocity, and veracity. So when we say the volume, of course, it is a huge amount of data, but it is not only one characteristic of the big data. So here we have the different format of data from various sources. We extract the useful data from this big data, which is known as the value. Then we have the velocity, like data is updating very fast. Data updation mechanism is very fast, because here the sensor network, sensor data from the ground and space, they continuously it is basically coming to our database system. Of course, the social media or the data generated by clouds are also playing very important role here. The velocity, then we have the veracity, lot of inconsistency, because lot of uncertainty is involved in this data. So by combining all these characteristics, when a data is qualifying, then it is called as a big data. So here the 4 B's are very important: volume, velocity, variety, and veracity. When I say the volume, is a data at rest, data in motion, data in many forms, data in doubt. These are very important things what we need to analyze in the geocomputations, and then only we can analyze this data, or we can extract the meaningful information out of this data sets. So here velocity is important, because you know that especially in geographical domains or geo data domains where we have the sensor network, either it's a ground-based sensor or space-based sensor, data is continuously flowing and it is coming to our database system. We require the advanced computation system to analyze this data. So real-time fast data is coming from social media, from the scientific instrument, from mobile devices, from satellite-based sensors, and so on. And these data are becoming very important for us, so that we should be able to analyze this data for our own application. So here, if you try to understand the big data from the space-based sensors are around nearly 6,542 satellites in our orbit, and out of this around 3,500 satellites are already active in nature, and you can understand how much data these satellites must be transferring from the space to the Earth. When we have this kind of data with us, you can see the variety of sensors, variety of satellites are coming here, and they are in our data centers. And geocomputation is playing very important role here, because ultimately we have to analyze this data sometime in real time, sometime in offline mode, or sometime in a on demand. So depending on the applications, the geocomputation technique will be applied on this data set, and so that effectively these data set can be utilized for different type of thematic applications. There are many challenges in this data analytics. It's storing unprecedented volume of data, describing what we have, that is a metadata, finding the what we use, identify unwanted data sets, data information quality strategy, data security, enabling real-time analytics of data, historical data, and so on. There are many challenges uh, uh, which are very very important, especially for the student researchers. They can take these challenges as an opportunity so that they can develop a new technique for geodata analytics or big data analytics and so on. So what kind of analytics we do here? We do like a descriptive analytics, diagnostic analysis, predictive analytics, and prescriptive analysis. These four type of analytics which are very very popular in the big data. So basically what happen and when, where and how it happens, what will happen and how, what should we do, or maybe actionable products, or how what action we should take so that we'll avoid this scenario or problem in futures. So these analytics are possible and are required, and to perform these analytics we apply the geocomputation technique. So these are the software tools which will be required or which are very popular. You can start from the like a NoSQL database like HBase. We have the Spark, a real-time processing technique, talent like software integrations platforms. We have Splunk like log analyzing system like Splunk, data warehousing system like Hive, messaging system like Kafka, Hadoop for data storage and processing platforms, data analytic platforms like Special Hadoop and so on. These techniques are very very important, and these are available in the open source community, and you can explore it, and then you can see how this technique can be utilized for big data and so on. There are many projects by Apache itself where the like a Special Hadoop for the geodata for the distributed file system. Then we have the GeoTurles, we have GeoMesa, GeoWave, and these tools are specifically customized and designed to handle the geodata. So whatever the big data challenges are there for the non-special data or attribute data are applicable in the special data as well, where we have the tools and technique available with us. That may not required. And what are the computation challenge here? Basically, one is the geospatial data analysis, processing and modeling. Cloud computations is another important challenge. Semantic sensor web, 3D and 4D GIS, participatory GIS, real-time simulations and virtualizations, geocomputation spatial analysis, spatial computation concept, and the computation spatial statistics and knowledge discovery, classification, predictions, and content-based image retrievals, data mining applications using pattern recognition, and so on. These are the important challenges in the geocomputation which are very very critical and important for the researchers and the student community. So there are many applications, like you can use these applications like healthcare and research, the automotive and productions, bank, insurance sectors, cyber securities, telecommunication, media, emergency and utility management, and so on. There are many domains where these techniques are used. The next part of my lecture is on concept of geo web services and online GIS. So here basically we are using the online platform for geodata processing or geodata geocomputations. Here the data is stored in centralized and distributed systems, and we develop the web applications, and by using these web applications different type of information system, distance support system or expert system can be developed here, and by applying these techniques on the geographical data or geospatial data, the online systems are already available. Typically, if you try to understand the architecture of the geo web services or geo portals, basically here it works like a simple web application, but we have an additional product called map server or GIS server, which basically process the geographical data or geospatial data and represent the output in the web compatible format. So this architecture is in practice, and here the geocomputation techniques are implemented or can be implemented in the online platforms. So we use the web 2.0 or GIS, and today we are talking about the now generative AI, where the web 3.0 is already entered in our life. So we can use all the technique together, and we can implement into geo applications. We use here a model called SO architectures, service-oriented architectures. In these architectures, basically we have the three tier architectures. One is a service broker, service consumer, and service providers. And this model is very popular in the web GIS or integrating GIS with internet. So in coming sessions, sometime we'll be discussing a little bit more about it. But SO architecture is very, very important for implementing the service-oriented web service-based system for geographical data. There is an organization called OGC, Open Geospatial Consortium, and OGC basically has designed the service standard for geographical data based on the SOA. This is a simple architecture where they find, bind, and publish three components are demonstrated how it is implemented in GIS, basically for data services, portal services, processing services, encoding, catalog services, and so on. And then finally, the outputs or APIs or web services are shared with the client. It can be integrated easily there, and then user can develop the application as per their own requirement. This is called Open Geospatial Consortium, and they have the vision like to develop a standard for geospatial web services. Different type of web service specifications are available from OGC called catalog services, processing services, encoding services. Then we have the data services, portal services, and other services. So here, in catalog, we have the catalog is like a clearinghouse where we basically design the standard for metadata. Processing is a real-time processing of vector and raster data where we have the processing services called web processing services, WPS. You can share the APIs or web service URL so that the user can process your raster and vector data on the fly without physical download of this data. Similarly, for encoding data as data representation purpose, we have the popular encoding methods like CTGML, KML, or SLD, where we basically represent the data in the form of the XML, extensive markup language, so that it will be readable and the user can customize, can modify as per their requirement. Data services is where actual data will be shared with the users. Portal for visualization purpose. Other services like we have the GeoXACML, GeoRSS, and so on. These services are useful basically for developing the smart solutions or smart GIS application. With that, I thank you all the participants for joining this first session. I hope the coming sessions will be also be interesting for you. So if you have any questions, you can post here. Otherwise, we can also take your questions during the panel discussion at the end of the program. Thank you very much.